Welcome back, all you cool cats and kittens. I'm talking about symmetry here. It's a different kind of transformation because it's not really transforming, but it's a way of looking at transformation. So let's look at symmetry. Excuse me. So symmetry is a rigid motion, reflection, translation, and rotation that maps itself. So it's just saying that, hey, if I were to do a reflection, a translation, or a rotation, I will make one half of this figure look like the other half of this figure. Now, for example, a star has reflection symmetry. So if I were to cut it down straight down the middle here, it's a horrible line. But this pretend is down the middle. This half can reflect over to this half, and it'll be exactly the same. So it has reflection stuff. Now translation's a little bit different. This is not as easy to translate that. So we don't have translation symmetry here, but we do have rotation symmetry. I can turn this and it look the same. I can turn it 1, 2, 3, 4, 5. 5 different times, and it look still like a star. So it has reflections and rotation symmetry. Let's look at this shape. How kind of these reflections does it have? Does it have symmetry? Does it have reflection symmetry, translation, or rotation? This one only has reflection. Reason being, let's rotate it and see what happens. So, okay, I'm starting my rotation right here. So if I end up, so I have to turn it a full 360 for it to get back to the exact same looking shape. So that's why this is not reflection. You have to rotate a full 360, so it has a rotation of 1, then it doesn't. It's not reflection. Just look at this one. It has 1, 2, 3, 4, 5. So it does have rotation symmetry, and it does have reflection symmetry. Now, the star is the same as this one, but I didn't go so in depth. But this one has multiple kinds. You can go down this way, this way, this way, this way, and this way. So for pretty much every point, you can reflect it. You can draw a line to see where they can reflect over. Now, not all 5 at the same time, but one at a time. So a line symmetry is when you're able to draw a line and it reflect over that line. So this star, all 3 of these have linear symmetry. Some only have it once, and some have it lots and lots and lots of times. In this case, 5 for this particular one. These are horrible lines. My bad, y'all. All right, so that's the different types of symmetry. So let's look at rotational symmetry a little bit more in depth. So rotational symmetry is, of course, that when I'm able to rotate this between 0 and 360, and I am able to get the same shape multiple times. Okay, now the order of symmetry is the number of times I'm able to make the same shape and that. Okay, and then the magnitude, meaning by how many degrees, how many times, the smallest amount of degrees, I can rotate it to get it. So for example, take a wild guess how many times I can rotate this and or how many times I can get the exact same picture in a full 360. Yes. Somebody said a number between 3 and 5. You're probably right. But not including 3 and not including 5. So for example, look how it is right now. So if I rotate this, that's 1, 2, 3, and 4. I'm able to go 4 times. I get the same picture 4 times between 0 and 360, including 360. So our order, our reflection for this particular shape is 4. Now to figure out the magnitude, so how many degrees it is per rotation, we just take 360 divided by 4. When we do that, we get 90 degrees. So it takes 90 degrees to go from here to here to get that image mapped onto itself. 90 degrees. Went too far on that one. Every 90 degrees, we should get the exact same image. We get the magnitude. So that's the magnitude. So let's look at these right here. So what is the order of order and magnitude for these? So for example, this particular one is a 1, 2, 3, 4, 5, 6 leaf petal. So more than likely it has 6 times. Let's see. Put a dot right there so we know where we start. No. I probably won't bring the dot. Yeah, I won't bring the dot. All right, let's go. 1, 2, 3, 4, 5, 6. So the order of this particular one is 6. Now to figure out the magnitude, we're going to take 360 divided by 6. That gives us 60 degrees. The magnitude of that is 60 degrees. Let's look at this one. Assuming these are all spread evenly. These are not on here, but let's assume they are. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13. 13 petals, so has an order of 13 more than likely. And to figure out that, the same thing. To figure out the magnitude, take 360 divided by 13. What do we get? If you had decimal number, 360 60 divided by 13, get 27.69. That's roughly the degrees of magnitude, and that's okay. So that is order and magnitude. Order is how many times can I get the exact same figure in a full 360 rotation, and by how many degrees can I rotate it to get that? How many degrees? The magnitude is at how many degrees. So here it only takes 60-degree rotation. I can rotate this just 160 degrees to get that image. So rotate it 160 degrees, bam, that's 60 degrees from here to here. There's our image. Now let's look at three-dimensional shape. There's plane symmetry, which works a lot like line symmetry. If I'm able to copy all points from one plane over to the other side, I get this shape. These both have plane and axis symmetry, and let's see why. Now, not always in the same manner. So for example, here, this has plane symmetry on this just straight up and down. That means I can copy all these three-dimensionally over to this side across this y-axis and has plane symmetry right there. Okay, this copies that. That's plane symmetry. I'm able to just copy those points. Same with the football. Football has plane symmetry this way, all these points this way, or no, wrong one. There you go. And it also has plane symmetry up and down. All the points down here, I can copy it over here, not including the laces. Let's assume the laces aren't there. And that will copy up and down like that. Now, this one does not have plane symmetry any other way. It only can go from this plane, this half over here, to this half, but it can't copy this. Or it'll look something like this. Like that. With this one, like an hourglass. Or it'll look like a diamond if you were to do the top half to the bottom half. Okay. But axis symmetry, so again, so go over plane. I should just finish plane. Plane, some objects only have one way. This one only has one plane. Copy straight down the middle. This copies that. This one has two ways. You can go horizontally, where all the bottom ones copy the top one, or vertically, where all the ones on the left can copy over all the ones on the right. Okay. Now, axis symmetry is if I'm able to rotate it. So, for example, this does have axis symmetry on one axis. This y-axis right here. If I were to spin it in a circle around this line, you'll get the exact same shape still. Same thing with football. If you were to hold the two ends of a football and just spin it, you still keep that same football shape per se. But you do not have it on this axis, because if you were to spin it this way, you get this like sauce weird top looking thing. You won't get the exact same, it won't keep the same football shape if it were to copy every single point, as if you were to stop it every second as it's rotating every degree. So it does not have it on the y-axis, but it does have it on the x-axis. So that's the difference between the axis symmetry. We're able to kind of spin it. So this is a spin and keep same shape / figure. Plane symmetry is just to copy the points three-dimensionally. So in all 3 dimensions, all this will copy over all over here. Same thing here. All this will copy all this down here. And then all this and copy all this over here. That's the plane symmetry. Hopefully that kind of helps out. It's just going to ask you throughout the homework, like, hey, what kind of symmetry is this? Ordering magnitude, so on and so forth. Does it have this kind of symmetry? Hopefully that helps. I'll catch you on a different day, y'all. Peace out.